Hi.
Hello, Winnie.
I think we're on. I was actually
Hello.
Hi, Dr. Thrun.
Hey. Hello.
Yeah, we're excited about the office hours. You got all the questions okay?
I have to find them. Sorry, I think I saw them, and then my inbox exploded with the 25,000 other inquiries of the day. When we mailed them to me?
Yeah, I emailed them through Winnie, I think, to you. She probably forwarded them to you.
Would you mind sending them to me again directly?
Yeah, what's the correct email address to send them to?
thrun@udacity.com.
Okay, I'll send those right now.
That would be very sweet. Thank you. Appreciate it.
Where are they?
That's basically the same question.
Okay, they're on their way.
See what I can find here. So thrun@udacity.com?
Yep.
Okay.
It just said it went out, so.
There you go. Okay, so. A*, competition self-driving car technology, full driving car. But perhaps you've done quite a bit of thing about economic impact of self-driving car. Good question. Students to learn become knowledgeable in quantum robotics to be competitive in language of engineer. Hottest current emerging research talents open source AI. Okay, that's good. Yep. Okay, a lot of repetition.
Yeah, I'm sorry I didn't organize those better for you.
Okay, no worries. And this is actually repetition over the years too. Okay, so when should we go live? In 3 minutes?
Yes.
Okay.
Now, can you see the chat window so I can just type questions into you if you need to, or the students can interact with you?
Hi guys, from Julio. I see that.
Okay. Okay, we are live apparently.
Okay, already 18 viewers. Okay, maybe I should stop browsing my internet mail here. Hi class, with you is Leo. And I'm Sebastian. Want to say a word, Leo?
Hello class, it's good to meet you all in a video hangout.
Okay, so what I usually do is I go over questions that we've collected, and we've collected quite a few, maybe too many, and go answer after answer. And up front, I'm very excited that you're all in class and that 20 of you choose to come in live. And I'm really excited about questions I get. So if you have questions, you can send it to me directly at thrun@udacity.com, or post them and collect them. And I hope we have more office hours like this. So in doing so, I'm going to look to the right side because it's my other screen is for questions. And I'm going to go through questions as they arrive. Here's one by William. William asks, conceptually speaking, how can A star be used in a non-grid continuous environment using, for example, Euclidean distance as a metric? How can A star be used in the real world? First of all, William, you're putting a finger at something really important here is most of AI deals with toy problems. They're very contrived, often very discrete, as finding a discrete path. And most of robotics and physical systems are continuous. And A star seems not to scale to continuous worlds. Luckily, there's a solution. Many years ago, a student of mine named Dmitry Dolgov invented something called hybrid A star. And what hybrid A star did is still approximates the world using a discrete grid. So it still says, okay, maybe the car occupies a certain square meter and it can only turn in 10-degree increments. So you can use A star to search the grid. But when the new grid cell is expanded, it keeps track of the exact continuous coordinates of that expansion. So while a grid cell might be this big, the car might enter at exactly here, exactly this heading. And then this location heading is being used to expand for the next search step. This is by no means optimal. You might miss solutions, it's not complete, and you might not find the shortest, but in many situations, like driving on a parking lot, you'll find a good path very fast. And then what Dmitry Dolgov afterwards in the hybrid A star, he used a smoother, a curve smoother, where you really try to take the skeleton devised by A star and turn it into a continuous trajectory, a spline in this case, and then really optimize for things like curvature and obstacle clearance. A smoother is typically a continuous optimization process that searches locally, so it can adjust the path a little bit, but it can't jump over an obstacle the way A star could do. So you get, by combining this kind of hybrid A star idea with this post-smoothing, you can actually get something that's locally optimal and often globally optimal when it comes to driving motion. That goes beyond the context of this concept of the class here. I wanted to keep it conceptual. But if you're really interested in bringing A star to physical vehicle motion, then I would recommend check out Dmitry Dolgov and my paper on hybrid A star. Yisan, thanks for being thrilled of having an office hour with me. I'm thrilled having an office hour with you. But here are the questions. What's your view of the current competition on self-driving car technology? Google Waymo partnering with Lyft, Baidu releasing Free OS for self-driving cars, like Google's Android for smartphones, Uber and Tesla investing in its own self-driving car research, and so on and so on. Should be open source, partnerships, API, what's right for the field? Look, the reality is this is anyone's guess, and I can give you my guess. Today, there is no self-driving car business yet, okay? And while we have no self-driving car business, each player has a chance to win, honestly. I would say in terms of technology, Google Waymo is most advanced. And obviously it was my own team a while back. And a lot of it will depend on how they steer, whether they build an open source system, whether they build lots of partnerships, or whether they decide to build their own taxi service. And I'm not in the loop of this, so it's all a speculation. However, I think there's many, many different applications of self-driving cars, not just one. So there's trucks, there's that picks you up as a taxi, there's systems that make aging people safer, there's obviously owner-owned cars, like the way Tesla does it, where you own your own self-driving car. And because it's such a big transformation, I think there's a lot of money to be made by many, many entities. So I would not write down the many startup companies in that space. They're kind of coming from behind, but they might eclipse the best companies today. And I would also not underestimate the pressure that's being built up on manufacturers right now, who are kind of forced to find their own solutions. So what's really happening, I would say, is a Wild West. I don't know how to bet on a winner, but in the next 2 or 3 years will be very, very telling. And it's a great field to get into. In fact, if you want to get into it, Udacity, which I, of course, work with Georgia Tech on this master's degree, has its own self-driving car offerings, its own nano degree that you might be interested in taking maybe after finishing this master's degree. What do you expect a full adoption of self-driving cars in the following market segments: ride-sharing, trucking, and privately owned vehicles? So these are the three fundamental areas. There's more fringe areas beyond this, but ride-sharing is one. So taxi like Uber, Didi. We of course work very close with Didi. Owner-operated, and trucking. Trucking is actually quite significant, and I'm a little bit sad that Otto wasn't able to pursue trucking further than they've done. Because as we all know, they sold to Uber. And Uber is, of course, much more interested in ride-sharing. I would argue the biggest bang for the buck will be ride-sharing, because it'll fundamentally change the economics of driving. So you can actually get to the point where every person's transportation bill will be lower than today. And that will be significant. I think owner-operated is a transitional phase. I have a Tesla. I love it. It's great. It's not fully self-driving, but it's doing a good job. But I don't think that the future will be in owned vehicles, honestly. Vehicles are very expensive. My Tesla cost me something like $100,000, crazy. And it's parked all the time. It's actually taking the parking space away. And the parking space it takes away, if I park at Google in a multi-level garage, it's also worth $100,000. So it's a huge waste. So I think the future has to be ride-sharing. And lots of stuff will happen. As a last pitch, I would not rule out complete new modes of transportation, like flying cars. And I don't know if anybody knows anybody working on this, but it could be an exciting topic. The next question, will self-driving cars potentially come self-recharging? Do you envision a future where self-driving cars can go for destination areas to recharge themselves? And if so, would it accelerate the shift from gasoline to full electric on Earth? Again, this is Yi-san asking the question. Insightful question. Interestingly enough, I think the idea of a ride-sharing system goes hand in hand with self-charging. If you look at today, the reason why people buy a Tesla is because they want a battery that carries the longest possible range they can ever cover. But if I had a ride-sharing service, almost every ride that I take is less than 10 miles. In fact, the average taxi ride in New York is about 2.4 miles. So with 2.4 miles of charge, you could serve the majority of rides in New York City, or here in Silicon Valley, maybe 5 or 6 miles in total. So in some sense, the cars could work on a much smaller battery. And for me as a customer who types in the distance I want to travel, the self-driving car picking me up could be charged at the right level for the trip, and that's it, which would be very, very nice. And it could disappear, and if it charges itself for a while, I, as a customer, wouldn't be upset about it because I could get a different car. From my perspective as a customer, all the cars would be charged at the right level. If I ever want to go to Lake Tahoe and need my phone and my battery, well, guess what? Maybe a super Tesla comes along, and for this specific ride, I pay a little bit more, but I get my charged car. So I think, in general, the ride-sharing idea is very susceptible to electric, and I think, in addition to economics, I think electric will become cheaper and much more competitive. It'll also be city cleanness, like smog and so on, that will drive the adoption of electric. So that I can see, with the vision of ride sharing, that electric will move much faster. There's an Elon Musk question we're going to skip because I'm not an expert on Mars. I guess the question is, Elon Musk and NASA have issued each their own plans to land humans on Mars. What level of impact would faster advancement of self-driving vehicle and AI-driven robots make to the successful colonization of Mars? I would say none. At this point, the problems in Mars are very different. Getting a human to Mars is actually really hard. We have never accomplished this. It is not because of lack of self-driving cars. It's lack of many other things, such as basic physics. Building a system that is safe enough that will bring a human safely back and can travel in a reasonable time, it's just not doable today. But Elon is going to solve it. If anyone of us, he's the best person to work on it. Brett is asking a question. I know you're not an economist, correct, Brett? But perhaps you've done quite a bit of thinking about the economic impacts of self-driving car. So what is the economic impact? What's going to happen? People can work in their cars going to work, or can they sleep? No more paid commercial drivers, housing choices, acceleration of uptake of electric cars, and so on. Great questions. When you start really thinking about it, the best person to talk to is Brett Templeton. Brett Templeton has a website where he speculates about things, what the self-driving car would do. So he, for example, says today's cars have to have a very stiff suspension because people like to feed themselves. But as a passenger, you would have a soft suspension. And he goes on to say, well, we should have beds in cars and offices. Why wouldn't we want to sleep in a car? And that would mean when I go to Lake Tahoe, why would I take a plane? I could just sleep overnight and wake up in the morning and be there. So travel would change. Certainly, we would be willing to have houses further away from our work, because you might get into the car at 4 a.m., fall asleep again, and be at work at 7, and that's acceptable. Whereas right now, driving 4 to 7 is very, very hard. So there will be changes on the way cities work. But most importantly, I think it's still the idea of car sharing. So right now, if you go to San Francisco, half or more of the people driving around are looking for parking, right? What a waste. Why do we do this? Why don't we just pick up a random car and use it and bring it back to where it was before? So I think the idea of car sharing will fundamentally transform cities in a really major way, which means there will be very few parking garages. There will be very few, actually very few vehicles in total compared to today. And instead, you can drop yourself off in front of your office or your favorite restaurant in your house, and the car moves on, does something else. It'll be a massive economic change. Also, in fact, truck drivers, another one. Truck drivers is, I think, the most frequent job in many states in the United States. There's more than 1 million, I believe. I don't know the exact numbers, but they will obviously be affected. Okay. R. Chase Adams, I have the question. Following this class, what would we recommend a student to do or learn to become more knowledgeable in current robotics AI topics, or to be competitive in landing a job as a robotics engineer? I'd argue this this master's degree is a great step to become competitive, and you're getting it from one of the most prestigious universities on the planet. What it does not do is it doesn't turn you into a robotics engineer. So you get a broad overview of computer science. You learn about theory and databases and compilers and all the things. In addition, you learn about AI, but not very much. If you want to deepen your knowledge of AI, my best answer is, of course, the work we've been doing at Udacity. We have about 4 or 5 nanodegrees out in this field, from deep learning to robotics to self-driving cars. In fact, if you want to become a self-driving car engineer, our program has been loved by many, many thousands of students. But do this after the master's degree. Don't do it in parallel, because the master's degree is a lot of work, and you probably have a job on the side that you also have to, and possibly a family that you need to attend to. David asked me a question. In the probabilistic methods we are learning in this class, system developers have to encode assumptions about the world, like the state transfer function F. Google's DeepMind uses a very different model-free approach with their project that learned to play Atari 2006 games using reinforcement learning with deep learning. In autonomous vehicles, some companies, like Common AI, are pursuing that model-free approach. How do you see the different strategies play out going forward? It's a phenomenally great question. The ability to predict things is something that's baked into many AI systems in a way that's actually bordering unrealistic. It is a fair game in gameplay. And funny you mentioned DeepMind, because in AlphaGo, which is the most recent and most famous game, they obviously know the next state function. They know what a board move does, right? So they don't do illegal moves. But in board games, the next state function is trivial. And it's one of the niceties of board games, that you can know the rules of the board exactly and still have a hard time playing it because of combinatorics. In the real world, the next state function is almost unknown. And I would say AI research have leaned too much in the past on assuming it's just known, and devised many, many methods. In probabilistic robotics, it's a softer version. It's assumed to be known somewhat, as in you have a probabilistic model. And you can go as far as and making your probabilities meaningless, in which case it's unknown. And you still can devise results from it. But yeah, I find these new methods, specifically deep learning and deep learning reinforcement learning, very appealing. And I think they're really important. So if I were you as a student, I would pay a lot of attention to those methods. I think they're much more natural, and they're also much more related to the way animals and humans learn. I don't think we have this chess plan in our brain about how the world evolves. We do a lot of stuff intuitively. Actually, much more than we sometimes give ourselves credit for. We do stuff intuitively and often use language to reason about it post the fact. But what actually was happened was an intuitive reaction. That is a very strong contrast with artificial intelligence, the way it is historically, where the model and the prediction and planning and so on has played a really important role. So I'm super excited about what Comma AI is doing, what we're doing here at Udacity with with self-driving cars because it's very much learning-based and has very little in the way of having an exact model. Okay, Sheila is asking a question. You had a comment or? Nope.
No.
All right, just patiently waiting it out. I love the fact we have matching shirts today and a somewhat matching haircut. But you have more hair than me. You win. Okay. Like to ask questions, Dr. Thrun. Are there still any technical challenges and roadblockers in the autonomous car project that are preventing them from going real? And the answer is yes. And I give you a few. The one that's uncomfortable, we can't do much about, is the long tail problem, which is it's easy to make 99% work. It's hard to make the last percent work. And in the last percent itself, it's easy to make the first 99% work. But then the last percent of the last percent is even harder. And these are these like ridiculous situations where a stroller runs to an intersection, or a deer commits suicide, or stuff happens like overnight a road got rerouted somewhere else, that are very rare, but in totality are still frequent enough to make it so that even the best teams have not yet launched massive technologies into the consumer market. But there's easier ones. For example, we are able to drive with our eyes only. So computer vision only driving is mostly unsolved. And that's where the most progress is being made right now. Low-cost sensing. What's also pretty much unsolved, honestly, is driving in a foreign country. Like right now, the Waymo team, which I used to run, uses extensive maps. And the rationale at the time was, which I think is correct, that you only have to drive a road once, you have a map, and then from there we can drive it forever or for a long time. So mapping is very cheap. But it would be great if I could send the car to places that never met before. The way you pick up a rental car and you're able to navigate just fine based on, say, Google Maps. So that's an open problem. And then I guess there's all kinds of other variants. Like we have competitions here at Udacity where we make cars race. I'm a firm believer a robotic Formula 1 car would beat every human driver, and so would a NASCAR car. But no one has built that yet. So it'd be really fun to do. So there's good challenges in my opinion. Then there's HCI challenges. Once you have the car drive itself, how do you engage the person? How do you hand off if you want to hand off control? Maybe you have a car that can drive 95% autonomous like a Tesla, but not 100%. There's all kinds of interesting problems along the way, but progress is being made very fast. So you have to jump on the bandwagon to be relevant. Carlos Laguna. Let me read this question. I'd like to know Dr. Thrun's opinion on the Udacity self-driving car nanodegree in the context of OMS-CS. I'm sure there must be a lot of things in common, but the program will diverge or complement each other. So the OMS-CS, which we built with Georgia Tech, really focuses on Georgia Tech instructors. And for me to even have the right to instruct here, I had to become an adjunct professor at Georgia Tech. And Georgia Tech has complete authority over the content of what's being offered. And Udacity very much behaves like a partner, but also we build content, but Georgia Tech is the boss. It's also a program that's very much focused on computer science, and it's very much a beautiful copy or replica of what you would learn on campus, and to the point that the degree is identical to the campus degree, which I love, and I really admire Georgia Tech for doing this this courageous step. The self-driving car nano degree is very different. It's much more focused. And it's not built by college professors. It's actually been built mostly by industry people. The way they approach a nano degree is that we are focusing very strongly on the job that follows. So we go to companies that are looking for talent like Mercedes and Uber ATG and many others, and ask them, look, on NVIDIA, like what type of skills would the students have to demonstrate to really impress you? And those things become our project. So it's not me, the professor, who dreams up that'd be a great project. It's really our partners who say, we really need somebody in sensor fusion. We need somebody in quality assurance and so on, and system reliable engineering, things that would not normally show up in a curriculum if just professors thought about it. There's downsides and upsides. The upside, I think, is that people have a much better chance to find a job afterwards in the chosen field. The downside is very focused, so you're not going to get the same breadth as you would get in a Georgia Tech master's degree. But I bet some of you are taking multiple things, and I hope some of you are trying out another degrees. And I hope you enjoy them as much as I hope you enjoy the Georgia Tech degree. Obviously, I have no split conflict of interest here. Should I like root for the Georgia Tech degree or the other degrees? I think they're all good. I think they're all ways for you to learn something new. And again, if you elect to enroll or apply for the self-driving car nano degree, then what you'll find is a much more focused, specific education to become a self-driving car engineer and find a job here in Silicon Valley or similar. Okay, how are we doing in time? I guess we're already 20 minutes in. Dominic asked a question. Many problems in AI that deal with acting optimally in the world use big data and computer-intensive solutions, machine learning, and so on. Are there cases in your experience where knowledge-based solution, which rely on having knowledge representation reason, have been used to good effect in situations where the resources of data and computability are significantly constrained? So, just to summarize this, the observation is there's lots of data and computation that's very hot right now. Could it be for learning, like deep learning, or it could be for optimization, like or estimation, like particle filters or genetic algorithms? But the question is there other cases where you can't afford computation or you don't have the data, where you could use rules instead and expert knowledge? The answer is yes. And funnily enough, it's yes historically, in the sense that when I was a grad student, artificial intelligence was all about expert systems, or maybe undergrad student. My good friend and colleague Ed Feigenbaum and many others had kind of invented this idea that you go to an expert and you quiz him long enough to build rules that you can chain those rules together and find new answers to new questions. He built an expert system called Mycin, which was a medical expert system. It could do diagnostics, and he was able to diagnose complete new diseases by putting together a large rule set from experts. That was the state of the art in AI in the 80s and 90s. And it was really this kind of introspection of our human intelligence, the pinnacle of human intelligence is thinking. So why don't we build a machine that can think? And think for us means we can take rules and chain them together and find new solutions. That's why search is so important, knowledge representation, logic. These were all the topics that were important when I was a kid. In fact, the biggest problem in AI at the time was called the frame problem, which you'll never hear about, and you don't know what it is because it was completely insignificant from today's perspective. But back in the day, it was to do with inference and closure of inference, when you went from like state-based systems to logics, and it was really hard, and people had to learn about it, and you can get a PhD writing about something called the frame problem. And then time moved on, and what really happened is computing got cheaper and storage got cheaper, and we started collecting bigger data sets. And then all of a sudden, we found that learning from data trumps, no pun intended, these big rule sets. In fact, there was a very famous program by Doug Leonard, who taught at Stanford and started a company called PsychCorp, where he felt if you take all of the knowledge of the world together, enough of it, and build this huge inference machine, then it would just do everything and become really smart. And what came out is, even if you spend 10 or 15 years with many engineers writing all the rules in the world, it doesn't get smart. It never became smart. It didn't become smart because it's really hard to string all these rules together. Like they all have different names and different attributes. They don't quite fit together, and language is very fuzzy. So in that age, like late 90s, early 2000s, at some point we realized, oh my God, learning wins, probabilities win, fuzzy inference wins. And of this emerged, of course, today's enthusiasm about deep learning. So today I would argue there's very few examples where rule-based systems in AI have the upper hand over machine learning. However, I think going forward, the combination of both would be great. So one thing I would love to see solved is I'd love to have someone build an AI that reads all the books. Right? There's not that many books. There's maybe 100 million books or whatever the number is. Reading them, Google scanned them all, so you should be able to read them all. And there's a lot of stuff in these books, and the stuff is encoded in rules and like sentences and so on. Might not be the type of rules that AI researchers like, but why can't we build an AI that could read all the books? Because if we can read all the books, then you're so much smarter than all of us. And then a small amount of data might make you even smarter. I mean, who knows? If you read all the books, maybe we can turn AI into an Einstein that really discovers fantastic new theories, as opposed to what we do today, where AI is just very repetitive and very remedial and just does the same thing over and over again. So if you're listening to me and if you're a superstar student, try that out and see if you can build an AI that can read all the books, and maybe start with one domain and then work your way up from there. It'd be fantastic. You could basically build the next Google if you wanted to, if you could just read all the books. So many problems are open there, to be honest. Okay, Michael, let's see. Can you briefly touch on how you would apply the fundamental concepts of this course or your work in general in industries other than robotics? For example, application of carbon filters in finance and economics, or search algorithms in supply chain optimization. I could give you a multi-hour lecture how these methods apply and also how they don't apply. Part of the class is state estimation. It's like trying to understand what's going on. Every airplane, every car, any manufacturing process, anything doing with time has an inherent state estimation problem. So you find state estimation in your telephone filters that filter your phone messages to maximize the transmission capacity. You find state estimation in the elevator that tries to stop exactly at the right level and has to, over time, understand the drift and the wear and tear of your elevator. You find enormous amounts of state estimation coupled with things like PID control in pretty much anything around you that moves. If you have a way to, I don't know, electronically actuate your window wipers, there's now a system that estimate over time how much wear and tear exists and compensate for this. If you look at Amazon warehouse fulfillment centers, there's these robots that pick up shelves and bring them somewhere else. They do constant state estimation to understand what the tire pressure is, how the tire pressure affects the robot trajectory. In fact, the idea of tire pressure measurement to state estimation is also inherent in cars, where your tire pressure gauge also uses a state estimator, looks at small variations in the wheel dynamics to understand, to infer from it what the tire measurement really is, tire pressure really is. Many methods. The second part is generally optimization, planning optimization, whatever you call it. So the question here was, for example, in supply chain optimization, a huge field of AI deals with supply chain optimization. You're running a factory and you have stuff coming in and stuff going out and machines in the middle and they break and people are not showing up to work. And you have to constantly reroute and build a plan that maximizes the productivity of your plant. That in itself is a huge field. And because factories are so important in the world, there's a lot of money tied to the idea to be able to do good supply chain management. That's actually the sweet spot of a lot of AI, because these things are often very discrete and not very continuous. So the methods, in my opinion, are very pervasive and can be applied to many problems. Internet of Things, transportation, of course, robotics, but even small things like speech recognition, or bigger things, speech recognition on your phone, language models. I have a student right now working on AI trying to reduce the amount of work that our sales force does here at Udacity, and he also uses state estimation in certain senses to make better decisions. I always thought of robotics as an example when I taught my classes, as a fun example, something fun to do that has like the AI wholeness, it has all elements of AI, but AI has been massively successful in many other fields, including like chip design, for example, where AI systems are being used to very cleverly quiz chips to see if there's a design flaw, because chips are way too big to test every single combination these days. Let's see, Wayne, thank you for your time, busy schedule. Oh, thank you, Wayne says there's some very positive things about me. Thank you, Wayne, appreciate it. Read the question. Are there major advantages between using machine learning versus artificial intelligence concept when implementing autonomous robot systems? And what's being used in the Mars rover? And he refers to Stanley as an early version of a robot. I don't know what's being used in the Mars rover. NASA has not been super famous for being crazy innovative, because the cost of a failed mission is just so insanely high that they'd rather typically go slow than fast. And there's nothing negative about it. It just happens to be when the cost of failure is enormous, that you end up not using the latest technology as fast as when the cost of failure is very low. The relationship of AI and machine learning, the question is, are there many major advantages between using machine learning versus artificial intelligence concepts? The reality is, I think machine learning is eating the breakfast, lunch, and dinner of AI these days. That's the reality. I mean, almost all the interesting progress is data-driven. And when you step a step back from the concepts we teach and ask like the bigger question, then I would argue there's a fundamental restructuring in which we program computers underway. That's actually more important than just AI and machine learning, which is any software engineer, any way that we program a computer in the past, we sit down and meticulously, for every contingency, think about what is the right rule. And we write this incredibly complicated kitchen recipe. Like Android is 12 million lines of code of kitchen recipe to just for every situation figure out what the computer do. We make the task so simple the computer never has to think, right? So we figure everything out. And because it's so hard to write a kitchen recipe of like 12 million lines of code, we pay software engineers lots of money and we train them very, very well in this master's degree and many others. I think the big transition now is that we now let the computer infer their own rules. So instead of giving them the rules, we give them the data. And data is just data points, and the computers now have to figure out the in-between by themselves. It's a bit like when you compare human learning. I mean, we don't spend the first 18 years of our childhood being instructed by our parents for every possible contingency, right? Our parents don't write a 12 million line kitchen recipe in our brain. Even some of them might want to, but they don't do this. Instead, we just run around and we fall over and we get up again and run into something and we insult somebody and apologize because, oh my God, bad data point, shouldn't do this again. And then we grow up, see things, and we perceive things, we make decisions, and we have our physical agility. We cut our finger at some point, it heals, and it's really hurt, but we're not going to do it again. So we learn. I think that what we see now is the very first wave of bringing the same idea to computers, where we can now train computers, for example, to detect skin cancer. Instead of telling them what skin cancer is, just show them like 100,000 images, and the computer figure it out by itself. And that's just very revolutionary. It actually means that a good chunk of your degree will be obsolete at some point, because at some point we're going to train our computers instead of just instructing them. And training, everyone can do. It's much easier. So computer programming will become easier, not harder in the future. And that's where I see the trend. And that's, I think, where machine learning is just basically now outpacing conventional programming. The ability to learn from data is basically unlimited, and we're just scratching the surface right now. I think 10 years from now, we'll be shocked how much more can be learned. Okay, let me move to the next question. By Katon Monday, who is excited to ask me a question. I'm excited to have you in the program. He has no formal training in CS robotics, but in a curiosity how these two subjects relate. So here's the question. Sorry, I'm reading as for more text that I want to read all of it. In a complex system like Stanley or the Google self-driving car, how is domain knowledge used? Is it something that can be thought of as a whole system level, or is it used at a more piecewise and component level, where the car has to recognize in a specific state, a specific task, the knowledge being used? So the question of how your domain knowledge is being used in a self-driving car defies a simple answer, because domain knowledge comes in many, many different variants. Perhaps the most obvious one are the maps that the car acquires and the cars share. So each car is equipped with a global map, and the map is very, very detailed. It has every little obstacle and every lane marker and every traffic light and every intersection where we could expect pedestrians and every speed limit. So there's a lot of data. And that data is, of course, maintained by the cars, is updated over time and distributed across these cars, and it's essential for the car's success in driving safely. But there's also domain knowledge, like they know what a stop sign looks like, and they know what various other signs look like. They know how a pedestrian looks like. There's knowledge encoded. They know how a pedestrian walks, right? What do they typically do? Like, they're more likely to want to cross an intersection when they're at an intersection in the middle of a street, or halfway between intersections. And that is much more implicit in the rules that the team has coded in and the learning results. And it's very hard to dissect, but it makes an enormous amount of the capability of the Google self-driving car is actually encoded in their knowledge. I want to bring this up because I want to contrast this with what people commonly call domain knowledge in AI. Commonly, it's in AI, it's meant to be rules. It's meant to be what's called an ontology, like a set of rules that describe something and that you can do inference over. The domain knowledge in a robot system, it's much more baked in, implicit, hard to tease out, often hard to find a rule. I did a recent piece of work with my students on finding skin cancer using deep learning. It was published in Nature earlier this year. And we just applied a neural network to find skin cancer to show that we do as good as the best physicians. Turns out it's easy. It's very, very easy. And somewhere in this network is the rule what a skin cancer looks like, right? If you go to a doctor school and want to become a medical doctor, med school, and learn and want to become a dermatologist, there's a rule called ABCDE. It has to do with like the fuzziness of the rim and color and the structure and the growth rate. And that rule is deficient. We do much better using these implicit rules that you learn from data than the fake manufactured rule that we use to teach other people. So leave it at this. But yes, domain knowledge is massively used. How much sensor redundancy is used in a system like the Google self-driving car? And how does a system like that respond to sensor failure? Does it try to detect sensors that are drifting or have fallen out of calibration? So one of the key things you build in is a massive self-monitoring system into self-driving car where you monitor every component and try to find failures as they occur. Most failures are easy to find. The way most sensors fail is they just stop working. It could be that it just broke, or the power supply broke, or we had a case where a very large moth ended up on the radar and blocked the radar transmission. And you find those failures easily. Past this, there are failures that are harder to find, where maybe your sensor is more erratic. And when I ran the Google team did was to do a lot of cross-check between different sensors to just see that the sensors themselves would fit other sensors' predictions. Each sensor has an inherent entropy, which is how much new information it provides. And when the sensor's entropy goes to the roof, it's probably broken. It's probably doing something random because it's not very consistent. So that's something that is baked in. Really, when you build a large-scale system like a self-driving car, you will find spending at least a third of the time on self-monitoring, trying to figure out when your stuff breaks. And then you want to build a system that informs a human safety driver that something has failed, so the car is less likely to cause a collision. In the current state, how quickly are autonomous driving systems able to adjust to changes in vehicle performance, like a hydraulic system leak or failing? The answer is, for those that are included to be worked on, yes, very fast. But there are failures that, at least when I ran the team, we hadn't really addressed yet. For example, we had never really addressed the flat tire problem. And the flat tire problem is solvable. So if you go to Amazon fulfillment center, they purchased a company called Kiva, which I mentioned before. And they have an estimator to understand tire pressure that is really, really fast. And in doing so, they can take different tire pressure and different loads and still have a very accurate motion by the robot. You have to, unfortunately, anticipate those failures in most parts to find a good way to react. There's no good technology that would take a failure you never encountered, never thought about, and give you a great outcome that I'm aware of. Maybe future learning systems can do this, but today's systems, to my knowledge, are not there yet. Okay, Timothy Thomas. So he's describing a situation that happened to me as he drove his car. I was sitting in traffic, barely moving, when I heard an ambulance siren. It was in the right lane. Behind me, I could see cars in the left lane starting pulling to the left, and those in the right pulling to the right. I could not see the ambulance, but inferred from other cars were doing was coming in the middle, and so on and so on. And it came through, and about a quarter mile later, we came to an accident which was in my lane. There was a police car in my lane with the lights on the switch lanes to get around it. There's quite a bit of aggression because the folks on the left didn't really want to let the people over. There was broken glass and debris in the road, so I went even further to the left to avoid it, driving off the road a bit. Then back to my lane and home. So the question is the car autonomous car able to handle the scenario, or maybe parts of it? Timothy, good question. More and more so, but not to the complexity you're describing. I mean, obviously, when all cars are self-driving, you'll never see an accident again, we hope. And this will never occur again, and there won't be any ambulances necessary. So hopefully that's the right solution. But in between, it's an issue. In fact, in California, the legislature has required that cars that are released for commercial products in that space are capable of handling the situation. And I am not aware of a single company has even applied for that permit. And I believe part of this is the inability to handle situations like those. One solution, in my opinion, would be to build a car that's remotely pilotable, where the vehicle will understand something strange is happening and give over control to a remote individual and have the remote person resolve it. I think that'd be the easiest way forward. I think it's completely doable. There will be latency issues and so on, but I don't think these are split-second decisions. These decisions are somewhat deliberate. They could be handled within a few seconds. Other than that, I think these are the, when I said in the beginning, there's like the first 90% is easy and 1% is hard. And about this 1%, the first 99 are easy. And that 1% of 1% is even harder. You're now in the 1% of 1% of 1%. And these are really, really hard. I would assume that a self-driving car today would stay in the lane and just be there blocked and block the ambulance, and the ambulance would get very mad at them. But that's, and of course, we have safety drivers in these cars, so they would, of course, manually take over and do the right thing, and they would be counted as a critical intervention and had to be reported in California to the legislator or regulator. Okay. Let me skip forward a little bit to Michael Tiranian. Currently, there's an open debate regarding the need of advanced and expensive sensors for autonomous driving. On the one hand, there are companies like Waymo, Cruise, Uber, and others who use LiDAR sensors. Others like Tesla and Comma use cameras. What are your thoughts on whether advanced sensors like LiDAR are necessary to achieve proper localization and perception of autonomous driving? I've been blown away by the progress with cameras. So I'm a big fan of placing most of my eggs in the camera. But you know what? I think LiDARs are expensive right now. They'll be cheap tomorrow. And they add another layer of safety. I would not want to build a car entirely without lasers. I think it'd be stupid. I think what we should do is we should really drive forward the laser or LiDARs as a commercial product. If you look at radars, they used, when I was a student, they used to cost $60,000 to $100,000. And the reason is there wasn't really market for it. You would order one and you get it like 3 months later, and the serial number would be number 0004 handwritten. And now they cost between $60 and $80 from tier 1 suppliers. There's nothing magical in a radar. It's relatively simple to build once you know what you're doing. There's nothing magical in laser. It's very simple to build. In fact, you can buy a laser without scanning capability today on Amazon for about $100. Just type in Arduino laser. You get a device, maybe $120. You can connect to your Arduino computer and get data range data. There's nothing magical. They wouldn't be able to scale. So my prediction is it's going to be cheap in the future, and it's not a bad idea to strategize among this if you're someone with deep pockets like a Waymo or a Tesla. Okay. Heimdall Woods. A group of my friends participated in your 2011 AI MOOC, the worst I ever made. And I'm a big fan, and so on and so on. Thanks for sending me questions, Heimdall. How do you foresee hardware, software, and approaches developed to tackle self-driving car problem being leveraged into newer existing markets outside the field of transportation? Have you seen examples of this already happening? So as I mentioned earlier, the self-driving car is of course comprised of maybe 4 or 5 components. It has a very strong mapping component, a state estimation localization component, a planning, path planning component, a controls component, and of course, to a lesser degree, user interface component. These core technologies are being found in many, many, many other domains. For example, in transportations, you find them in things like planes and trains and so on. But you find them, for example, Internet of Things. If you want to have a smart home, the home's ability, for example, to understand who just entered, and is that person entering allowed to enter? Should I maybe trigger a message that someone new showed up in your home? Is a state estimation problem? It's kind of similar to the question, is there a pedestrian in front of me? And should I avoid the pedestrian? The technology being used for the most advanced smart home cameras today, or the technology used inside Amazon Alexa, is amazingly similar to technology being used in a self-driving car. It's different data sources, different things you're trying to estimate, but they're still trying to estimate stuff from data, and machine learning and state estimation are big components of that. Having said this, if you were to take the self-driving car nanodegree, you will, of course, have as examples, always car examples and nothing else. That's just the way we set it up. But there's huge overlap with the AI nanodegree we have, robotics nanodegree, and many other nanodegrees we are already launched, are developing. Okay. Oh yeah, here's a kid. I saw your Twitter picture on the Kitty Hawk flyer last week. From the context of AI and machine learning, how can we use technology to mitigate the regular fears like the FAA, as well as substantially reducing the amount of time and money a flying car operator would require to certify themselves as a pilot? Okay, what do you believe is the biggest challenge for this technology to be adapted mass in the future? So this is about my side job. I obviously work on little things that fly. Let me see, do this. This picture has not been really made public, but that's me a few months ago flying. It's a fantastic playground for AI. What we've been doing is we try to make it so that all the hard problems of piloting a vehicle are done by AI, but the easy and fun stuff, like the going forward, backward, diving, left, right, and turning, is full under user control. We are obviously made clear that we're launching this. We're going to sell it later this year to people who are willing to pay for it. It's not going to be cheap in the beginning, hopefully cheap over time. And we believe that we are obviously working with the FAA that we can accomplish a great synergy. The FAA has carved out an area of vehicles called ultra-lightweight vehicles, where this vehicle fits, in our opinion. And we hope it to be flown just very low and slow over water, so if something bad happens, that no one gets hurt. We've done over 1,000 flights so far. So good. Let's knock on laptop. But yeah, it's a fascinating field. I actually do believe that long range going forward, that a lot of transportation will move in the air. And the reason is, even if you build self-driving cars, the air has so much more space. And in some sense, it's like you're going to be faster. You're actually going to be safer in the air, and obviously you're going to be cheaper in the air. It's kind of intuitive, but most of the energy in transportation is not used for lifting you up. It's a plane. It's actually used for drag, for flying forward. If you take a plane and switch the engines off, you go on like this and not like this, which means most of the energy is being used for drag. But it's a different topic for a different class. I'm not teaching self-flying cars here. I'm teaching robotics here. Last question by Cassius. How does the interview process for a team like the self-driving car team at Google differ from standard technical interview processes at large companies? Any recommendation in how to stand out as a candidate? For interviewing Google, and specifically Google X, highly recommend watching our Udacity talks with Astro Teller, where I quizzed him on the same session. And he actually gave really great answers what makes a candidate successful. Google has done research on technical interview and correlating it with an outcome in terms of employee performance. Google has hired over 40,000 engineers in its history. All of those underwent a radical interview process, often answering technical coding questions with 10 different interviewees. All of those result in a score between 1 and 5. 1 means over my dead body, 5 means walk on water. Most people are in the range of 3 to 3.5 to 4. And then over the years, these engineers, those who stayed, get quarterly performance scores. They're heavily calibrated among multiple managers. They're being used for promotions, so you can really graphically understand how well a person performs inside the company. The reason why it's so meticulously done inside Google is because Larry and Sergey love data. They're data scientists, and they turned HR into a data science inside Google. One thing that they found, it's really interesting. So Laszlo Bock, who ran this as the head of HR at the time for about 15 years total, that there's very little correlation between interview scores and on-job performance. And that was blew our mind, blew everyone's mind. We can quiz people really hard on, like, can you solve this sorting problem in linear time? And some get it right and most don't. And we only hire the ones get it right. We don't get better performers. And the reason is good work performance is not just solving things on the spot. IQ is obviously a part of it, but it's so much more important that you're a good citizen, you work good with others, you communicate well, you're willing to go the extra mile, and you're part of a team. It's so much more important than just being sharp. And that's much harder to test. How do you test whether people are sharp? So one of the things that Google interviews test is actually, when no one looks, will you clean up the carpet on your own? Something like that. Will you go the extra mile? At Udacity, I love those people who empty the dishwasher when no one's looking. We have an award structure for this. We actually give people awards when they do something interesting. At AT&T, the mission is every day you do something that helps other people without being acknowledged for it. So if you want to, again, watch Astro Teller's video for interviewing, his answer was that two things. One is there anything interesting outside your given field you do, something fascinating? He finds that people who have interesting hobbies and are curious people do much better. And then he did a test with me. You can see this. He handed me an object and I had to do something with it. And when you watch this video, look at my reaction. and guess whether he would have hired me or not. And I'll leave it at this. I think I'm out of questions, and we spent almost 50 minutes on this. Do you have anything online? Anything you want to add?
No, I think we'll start collecting questions for the next office hours.
Okay. So normally I try to keep them at 30 minutes. Obviously today was 50 minutes because I don't want to torture you guys. But thanks for showing up and being here. I'm a big fan of you guys that you do this. I think lifelong education is super important. And honestly, I take great pride in what we do. So if anything we can improve, drop me an email. I love getting emails from my students. I know people are sometimes afraid doing this, but it's thrun@udacity.com. So feel most invited to send me emails. You guys are my heroes. Thanks for doing what you do.
Thank you.
All right, then I hit the stop broadcast button.
Yep.
Bye-bye. And thanks for your fantastic work, Leo. I appreciate it.
Thank you.